Good morning, students. This is Sridhar, Associate President, Ramchandra College of Engineering. So, already we discussed about that gate level modeling, some of the concepts in the gate level modeling. So, in that, we discussed about what is meant by gate level modeling, what are the different types of Verilog primitives present in Verilog HDL, and next one is the what are the truth tables of the Verilog primitives and some of the examples of the Verilog primitives. Okay, so these are the topics we discussed in the last sessions. So now I'll talk about that implementation of the gate level modeling by using this Verilog HDL. Okay, students. So I'll go to the implementation of the Verilog HDL. So here, if you observe this here I would like to implement these gate primitives by using this Verilog HDL here. Okay, friends. So here I would like to explain about that how to develop the simple latch by using this Verilog HDL here. So in the SR latch, so here I am considering the SR latch here. So in that, what are the inputs here? Inputs are known as the SB and RB are known as the inputs for this latch here. Okay, students, SB and RB are the inputs for this circuit. So that's why here I am describing the SB and RB are known as the inputs for this circuit here. And what are the outputs here? Q and QB are known as the outputs for this circuit here. Okay, friends. So here I would like to develop this implementation of these SR latch by using this Verilog HDL here. So what are the inputs here? Inputs are known as the SB and RB are known as the inputs for this circuit. What are the outputs here? Q and QB are known as the outputs for this circuit. I'd like to talk about that. So here it having the how many gates here? It having the AND gate, not gate, AND gate, not gate here. Instead of that, we can able to develop this circuit by using the directly one AND gate. Is it correct or not? So I can able to develop this instead of this and not. I can able to develop the directly one NAND gate. Here also I can able to develop the instead of this and not gate. I can able to develop the one NAND gate here. Okay, students. Here, let us talk about that. If suppose here this one is the let us consider the this one is the one NAND gate. So this one is the one NAND gate. Let us talk about that. This is known as the NAND gate here. NAND gate. Similarly, so this is also one NAND gate. Okay, friends. So here this one is the internal representation of this SR latch. So in that SR latch, so it performs some NAND operation, and this is also performs some NAND operation. So for this NAND gate, what are the inputs and what are the outputs here? Okay, students, for this NAND gate, what are the inputs and what are the outputs for this NAND gate here? So that if you consider this NAND gate here, I am considering this NAND gate here. So what is the input here? What is the input and what is the output here? One of the input is known as one of the output for this NAND gate is known as the Q is the output for this NAND gate here. Okay, friends, Q is the output for this NAND gate here. What are the inputs here? SB is the one of the input here. Okay, SB is known as the one of the input here. And next one, if you observe this, what is the next terminal here? If you observe this one is the what is the next terminal? This NAND gate is connected. Next terminal is connected to this NAND gate is a QB terminal here. So this output is feed forward to the input of this NAND gate here. So that's why for this NAND gate, Here QB is also can be taken as the input of the circuit here. Now I'll talk about this NAND gate. This NAND gate here. I'll talk about this NAND gate here. What are the inputs here? Inputs are known as the. So if you observe these RB as well as the next input. What is the next input here? This output is here. I am tapping this output here. Next input is known as the Q. RB and Q are known as the inputs for this NAND gate here. What is the output here? Output is known as a QB for this circuit. So if you observe this, QB is the output for this NAND gate here. So in that way, I can able to develop the circuit by using the which level modeling here. I am developing the circuit functionality by using the which modeling here. Can able to develop the by using the NAND gate. So that's why this is known as the gates. Here I am using the gates here. That's why this is known as the gate level modeling. Okay, friends. So this is one of the important concepts in our Verilog HDL. So we have the different four types of modelings we have. So in four types of modeling, in the second unit we talk about that gate level modeling here. Okay, so that's why I'm using the explaining the gate level modeling examples. So for the sake of this gate level modeling examples, I am taking this one is what is here flip-flops implementation. So this is known as the AND module. We are terminating the program by using this AND module here. Okay, students. So this is the design of flip-flop. So here I am designing the one flip-flop here. Now I'll talk about that RS flip-flop. Here I am developing the next one is known as the RS flip-flop here. So if you observe this, here also, here I am developing the RS flip-flop by using the same process. Here also, here I am taking the, so this one is the one NAND gate. That's why I'm giving this name is the, what is the name of this gate here? This is known as the NAND gate here. Similarly, so this is also another NAND gate here. This NAND gate and this one is the another NAND gate here. Okay, students. Here I am applying the inputs inversion. Here I am applying the inputs after inversion here. So we are getting the value is the Q as well as the Q bar value here. So that what are the inputs for this circuit here for this RS flip-flop? So inputs are known as the S are known as the inputs and Q and QB are known as the outputs here. Okay, friends, S sir, S and R are known as the inputs for this circuit. Q and QB are known as the outputs for this circuit here. So that's why I am defining the input S comma R. So here I am defining the S are known as the inputs. What are the outputs here? Q and QB are the outputs here. Okay, friends. So if you observe this here, we have to find the one common point. What is the common point here? Here I am defining the wire SS comma RR. Here I am defining the wire SS comma RR. What is in the wire here? It is a intermediate connection between the this gate and as well as this gate here. This is a intermediate connection between this gate as well as this gate here. So that intermediate connection can be represented as the RR. And next one, what is this here? This gate and this gate. This intermediate connection can be described as the SS. Okay, students. So that's why I'm defining the wires here. That way, we are defining the wires here. Now I'll talk about that knot. So instead of the defining the double not representation or double not gate instantiation, so here I am using the s comma ss. Here I am using the r comma rr. So here I am taking the one AND gate. Here I am taking the one AND gate here. Here also I am taking the another NAND gate here. So what are the inputs here? Inputs are known as the, what is the input here? Here if you observe this AND gate functionality, here I am taking the output, I am gathering the output from which location here, from this location. So that's why I am representing the Q, one of the input is known as the RR, one of the input is known as the RR, and next one, what is the input here? And another input is known as the Q here. So this output is feed forward to this circuit. So that's why RR and QOQ is known as the inputs for this circuit. Okay, RR and Q is known as the inputs for this circuit. What is output here? QB is known as the outputs for this circuit. Okay, QB is known, so that's why I am representing the QB is the output for this circuit here. So we are terminating the and next one is in similar way I am taking the another NAND gate. Here I am taking the another NAND gate here. What is the input here? One of the input, one of the output is the, so here if you observe this, what is the input here? So input is the SS bar. So input is the SS. And what is the next one here? What is the output here? Output is known as a Q here. So we are feed forwarding this output and apply to the another NAND gate here. So in that way, we are designing this RS flip-flop module here. Okay, students. So now I will go to the designing of flip-flops with gate primitives here. So already we are designing this SR flip-flop, SR flip-flop implementation by using the NAND gate. So this designing already, if you observe this designing is already we are implemented. This designing is already implemented. So in the last slide. So is it correct or not? So this is the designing what we are implemented. What we are showing in the current slide, the designing is implemented in this slide here. Okay, friends. Then why we are representing this one here? We are developing the circuit SR flip-flop. Those circuit can be tested by using this test bench. Okay, we are testing that circuit by using this test bench here. So whatever the inputs we are defining, that inputs can be defined as the resistors here. Whatever the outputs we are defining, that outputs can be defined as the wires here. Inputs are the resistor as well as the outputs are the wires here. So here I am instantiation the module name is SR flip-flop here. So that's why I have instantiated the module name is SR flip-flop. So whatever the inputs we are instantiation, those inputs are defined here. So this is known as a procedural assignment statement. What are the procedural assignment statements we have? So we have the procedural assignment statements are the initial, always, initial, always. These are known as the some of the procedural assignment statements used in our Verilog HDL here. So here I am using the procedural assignment statement is the initial. So initial begin SB and RB one tick B1 as well as RB one tick B0. And so we are starting this procedural assembly. We are instantiated this flip-flop by using these inputs here. So one tick B1, one tick B. So that means we are applying the 1 here and we are applying the 1 here. We are applying the 0 here. We are applying the 1 here. So these are the inputs we are applying to this SRB, SBRB, FF here. So for every 2 seconds, the inputs will be changes. So that's why here whatever the changes are occur, the changes can be displayed by using this dollar monitor. These are known as a system tasks we have. So what is the use of the system task here? To monitor the variables, to monitor the variables, to monitor the time, to display to stop the simulation. All these are the possible by using these system tasks here. Okay, so that's why here I am using the system task here, and after that we are closing the total testament by using this end module here. Okay, students, so this is the testament implementation of this one. So now I'll talk about this implementation of the D latch. How to develop the D latch by using this gate level modeling. Okay, by using the gate level modeling, how we can to develop here. So D latch. So it having the inputs. What are the inputs here? If you observe this circuit, these are known as the D and enable are known as the D and enable are known as the inputs for this circuit here. What are the output here? Q and QB are known as the output here. What are the wires here? DD. So that is nothing but the this input is applied to this inverting. So that's why that value is known as a DD here. What are the wires here? S and R known as the wires here. So if you observe in this diagram, so here I am taking the first NOT gate here. So what is the label of this NOT gate here? Label of this NOT gate is known as a N1 here. So that's why here whatever the inputs we are applying, that input can be inverted here. Next one, NAND gate. So NAND gate. So what are the inputs here? Enable and data terminal are the inputs for this NAND gate here. What is output here? SP is known as the output for this NAND gate here. And next one, taking another NAND gate. For this NAND gate, what are the inputs here? Enable, DLatch, and RB are known as the inputs for this inputs as well as the outputs for this NAND gate here. So after that, we are defining this SR flip-flop. After that, we are terminating the program. So in that way, we can able to develop the different types of implementation by using this gate level modeling. This way, we can able to develop the different types of implementation by using the gate level modeling. So that one is the D latch modeling. So in this session, we are implement the SR latch as well as the SR latch as well as the JK flip flop, and next one is the D latch here. So okay students, so now based upon this knowledge, so this is assignment for you. So based upon this knowledge, write an assignment. So write a Verilog module, write a Verilog module to develop T latch. Write a Verilog module to develop the T-latch by using the gate level implementation. Okay. Did you know that gate level implementation means that compulsory we should represent the total whatever the program we are developing. All the program implementations can be developed by using these basic gates only. All these are the developed by using only the which one here? Basic gates only. So this one is the basic gates. So if you observe these are also basic gates. So that means by using the gates only, we can able to develop the digital logic function here. Okay, we can able to develop the digital logic function by using the gates here. So that's why This is known as the gate level modeling here. Okay, students. So with this knowledge only, generally by using the, whenever if we want to develop the VLSI projects, in our VLSI projects, some modules are developed with the help of the gate level model. Some modules can be developed by using the behavioral model, so that we can mix those two modules by using a mixed signal modeling also. Okay, students. So these are the different methods to develop the VLSI projects here. Okay, friends. Okay, thank you.